A pilot initiates a missed approach. The airplane suddenly rolls and impacts the ground in a 17-degree, nose-down pitch attitude. An airplane on approach experiences pitch excursions of greater than 70 degrees. The airplane does not recover. An airplane is on an automatic ILS approach, but an error has been made with the autoflight system. The airplane enters a severe nose-high pitch attitude, stalls, and does not recover. Three different accidents, three different causes, but one common thread. At some point in each case, the airplane was upset and entered an unusual attitude. That is, the plane unintentionally exceeded the parameters that you, the pilot, normally experience in day-to-day operations. Every day around the world, tens of thousands of airplanes take flight. As you well know, an overwhelming majority of those flights proceed without incident. Airplane upsets are not a common occurrence. However, there have been many loss-of-control incidents in multi-engine turbojet airplanes. And since the beginning of the jet age, there have been a significant number of commercial jet transport accidents attributed to control problems. As you'll see, causes for airplane upsets are varied, and in some cases, difficult to agree upon. But one thing everyone agrees with is that once your airplane is upset and enters an unusual attitude, you may have little time to react. The actions you take are critical to recovery. With this in mind, airlines, pilot associations, airplane manufacturers, and government aviation and regulatory agencies feel it is appropriate that you receive airplane upset recovery training. This video will define airplane upset. We'll look at causes, and we'll review aerodynamic principles that form a basis for recovery. There's no doubt, you never want to be in a situation where your airplane has rolled or pitched out of control. But if you do find yourself in such a situation, the information that follows can play a vital part in a successful recovery. An airplane is defined as upset if it unintentionally exceeds the parameters normally experienced in line operations or training. Specific values may vary among airplane models, but the following conditions are generally agreed upon. Unintentional pitch attitude greater than 25 degrees nose up. Unintentional pitch attitude greater than 10 degrees nose down. Unintentional bank angle greater than 45 degrees. Or, even within these parameters, but flying at airspeeds inappropriate for the conditions. The causes of airplane upset are varied, but these can also be broadly categorized. Upsets that are environmentally induced, those caused by airplane components, those caused by human factors, or those induced by a combination of any of these. Interpreting and responding to rapidly changing environmental conditions is a constant way of life for the working pilot. These conditions can also lead to an airplane upset, although not all of them have a direct effect on the airplane itself. For example, a rapid environmental change may dictate a quick transition from VMC to IMC. During this transition, it's often easy to get distracted. Research shows that an upset is more likely to develop when the flight crew is distracted. Environmental conditions can also cause visual illusions, such as false vertical and horizontal cues. During such illusions, instruments can be misinterpreted, and again, the flight crew can be distracted. The biggest danger from environmental conditions, however, are those that directly affect the airplane flight path, such as the various types of turbulence a pilot might encounter. Industry study has validated that wake vortex turbulence can contribute to an airplane upset. Wind shear has also been extensively studied and is a known cause of upset. Mountain waves. Severe turbulence advancing up one side of a mountain and down the other is another environmental factor that can affect the airplane flight path. As is clear air turbulence, often marked by rapid changes in pressure, temperature fluctuations, and dramatic changes in wind direction and velocity. Other environmentally induced factors that can contribute to or cause an airplane upset include thunderstorms and weather conditions that result in ice buildup on the airplane. The best solution to environmental hazards is to avoid them when possible.
Moncton Center, Atlantic 250, requesting 20-degree deviation to the left for weather.
Today's airplanes are remarkably reliable, and malfunction of components or equipment that can lead to an upset are rare. Because of this high level of reliability, when these problems do occur, they can surprise the flight crew. Airplane component problems, such as an instrument failure or an autopilot failure, fall under this category. Again, the result can be direct, such as an autopilot failure resulting in a pitch moment, or there can be an indirect effect, if the flight crew has been significantly distracted by the failure of a particular component. Other causes include flight control anomalies and system failures that lead to unusual control input requirements, as might be experienced with an engine failure, failure of the yaw damper, the spoilers, the flaps or slats, the primary flight controls, or as a result of structural problems. Human factors must also be taken into account when examining possible causes. Cross-check and instrument interpretation is an example. Misinterpretation of instruments or a slow cross-check may lead to an upset.
You're cleared to 3.
Okay, starting down.
An upset can result from unexpected airplane response to power adjustments, automated functions, or control inputs, inappropriate use of automation, or by pilots applying opposing inputs simultaneously.
Hey, check your speed.
The autopilot's not holding airspeed very good.
You're in vertical speed mode.
Okay, I forgot. Go on flight level change, 240.
As previously mentioned, inattention or distraction in the flight deck can lead to an upset. This includes any type of distraction that causes the flight crew to disregard control of the airplane, even momentarily. Spatial disorientation, the inability to correctly orient oneself with respect to the Earth's surface, has been a significant factor in many airplane upsets. Other rare but possible human factors include pilot incapacitation due to a medical problem, or even rarer, a hijacking situation. A combination of any of these factors can also lead to upset. It's important to remember that we're trying to look at all possible causes here, no matter how remote the possibility. The fact is, it's sometimes this very remoteness that allows an upset situation to develop. Now that we've taken a look at the possible causes, let's take a few moments to review some key aerodynamic principles. These are the things you learned at the beginning of your flying career. You now react instinctively on the flight deck and rarely need to think about aerodynamic theory. However, in an airplane upset situation, these principles form the basis for recovery. We've asked the chief test pilots for Boeing and Airbus to assist us in this discussion. These are pilots who have taken their airplanes to the extremes.
When discussing large airplane aerodynamics, 3 words often enter the conversation: Energy, the capacity to do work. Flight path, the actual direction and velocity an airplane follows. And maneuver, a controlled variation of the flight path. In an airplane, the ultimate goal of using energy is to maneuver the airplane to control the flight path. The energy created by the thrust of the engines and the lift generated by the wings is controlled by the thrust levers and flight controls to overcome gravity and aerodynamic drag. In other words, flight controls give you the ability to balance the forces acting on the airplane in order to maneuver, to change the flight path of the airplane. The direction of the lift produced by the wings is independent of the direction of gravity. Two other important principles: energy management and angle of attack. An airplane in flight has two types of energy: kinetic, or airspeed, and potential, or altitude. You exchange speed for altitude and altitude for speed. The angle at which the wing meets the relative wind is called the angle of attack. Angle of attack does not equate to pitch angle. Changing the angle of attack either increases or decreases the amount of lift generated. But beyond the stall, the angle of attack must be reduced to restore lift.
Now let's look at the elements of stability. Movement around the lateral axis of an airplane is called pitch and is usually controlled by the elevator. At any specific combination of airplane configuration, weight, center of gravity, and speed, there will be one elevator position in which all of these forces are balanced. In flight, the two elements most easily changed are speed and elevator position. As the speed changes, the elevator position must be adjusted to balance the aerodynamic forces. For example, as the speed increases, the wing creates more lift. If the airplane is at a balanced in-trim position in flight, it will generally seek to return to the trim position if upset by external forces or momentary pilot input. This is called positive longitudinal static stability. We've all experienced this and are familiar with the requirements to apply pull forces when an airplane is slowed and push forces when an airplane speeds up. Changes in airplane configuration will also affect pitching moment. For example, extending wing-mounted speed brakes generally produces a nose-up pitching moment. Airplanes that have electronic flight control systems, commonly referred to as fly-by-wire, may automatically compensate for these changes in configuration. Thrust affects pitch as well. With underwing engines, reducing thrust creates a nose-down pitching moment. Increasing thrust creates a nose-up pitching moment. Airplanes with fuselage or tail-mounted engines, or those designed with electronic flight controls, produce different effects. Whatever type of plane you are flying, you need to know how the airplane will respond. The combination of elevator and stabilizer position also affects pitch. In normal maneuvering, the pilot displaces the elevator to achieve a change in pitch. The stabilizer is then trimmed by driving it to a new position to balance the forces. This new stabilizer position is faired with the elevator. If the stabilizer and elevator are not faired, one cancels out the other. This condition limits the airplane's ability to overcome other pitching moments from configuration changes or thrust.
Now, let's continue this discussion by taking a look at yaw and roll. Motion about the vertical axis is called yaw and is controlled by the rudder. Movement of the rudder creates a force and a resulting rotation about the vertical axis.
The vertical stabilizer and rudder are sized to meet two objectives: to control asymmetric thrust from an engine failure at the most demanding flight condition, and to generate sufficient side slip for crosswind landings.
To achieve these objectives at takeoff and landing speeds, the vertical stabilizer and rudder must be capable of generating powerful yawing moments and large side slip angles. Motion about the longitudinal axis is called roll. Control inputs cause the ailerons, and then spoilers, to control the airplane's roll rate. The aileron and spoiler movement changes the local angle of attack of the wing, changing the amount of lift, which causes rotation about the longitudinal axis. During an upset, there may be unusually large amounts of aileron input required to recover the airplane. If necessary, this can be assisted by coordinated input of rudder in the direction of the desired roll.
However, when a large transport swept-wing airplane is at a high angle of attack, pilots must be careful when using rudder for assisting lateral control. Excessive rudder can cause excessive side slip, which could lead to departure from controlled flight.
As angle of attack increases, aileron and spoiler effectiveness decrease because the airflow begins to separate over the wing. However, the rudder airflow is not separated. It remains aerodynamically effective.
In some aircraft configurations, there is a certain crossover speed at which full aileron and spoiler deflection is necessary to counter the roll due to full rudder deflection and the resulting side slip. Below this crossover speed, the rolling moment created by ailerons and spoilers is gradually unable to counter the rolling moment induced by the side slip generated by full rudder deflection. The airplane must be unloaded to reduce angle of attack, and the airspeed must be increased to maintain lateral control.
In contrast, very high speeds in excess of VMO and MMO cause control surfaces to be blown down, rendering them less effective.
The main concern at high speed, in excess of VMO and MMO, comes from vibrations and high air loads that may lead to structural damage. Other effects often include reduced effectiveness or even reversal of control response. Any pitching moment due to speed brake extension or retraction is more pronounced at high speed, and pitching effects as a result of thrust changes are less pronounced.
High-speed buffet is caused by shock wave instability. As the airplane exceeds its cruise speed, the shock wave that runs along the wing upper surface becomes strong enough to cause the beginning of a local separation or stall. This causes the flow over the wing to fluctuate, leading to rapid changes in drag and the position of the center of pressure. The ensuing buffet results in a loss of aerodynamic efficiency of the wing, which will impact the high-speed dive recovery. The buffet can be disconcerting and will normally not be symmetrical on each wing, resulting in a rocking motion during a pull-up. The pilot should relax the pull force if high-speed buffet is encountered.
Altitude and Mach also affect the performance of the control surfaces. The higher the altitude and Mach, the more sensitive the airplane is to control surface movements, making the recovery more difficult. Asymmetric thrust affects roll. When there is asymmetric thrust, side slip is created and thus roll. This is normally countered with rudder and lateral control. Obviously then, reducing an asymmetric thrust condition will also reduce the side slip associated with it. The definition of VMCA is the minimum flight speed at which the airplane is controllable with a maximum of 5 degrees bank when the critical engine suddenly becomes inoperative with the remaining engine at takeoff thrust. Below this speed, there is insufficient directional control. As the airspeed decreases, the ability to maneuver the airplane also decreases. During a full or deep stall, the flight controls become less effective because of the high angle of attack. However, the rudder remains effective at lower speeds. This can be good or bad. At speeds above stall, the rudder can assist the airplane's ability to roll. But at slower speeds, there will be a delay after application of the rudder before roll response becomes apparent to you. Also, the amount of rudder used and the rate at which it is applied is critical. The bad part is that at speeds approaching the stall speed, or speeds below the stall speed, use of rudder applied too quickly or held too long may result in loss of lateral and directional control and cause structural damage. At any speed, large aggressive flight control reversals can lead to loads that can exceed structural design limits.
Another consideration for longitudinal control is G-load. That is, the amount of load factor that is aligned with the vertical axis of the aircraft. In a level turn, or pull-up, the wing has to create more lift and the pilot feels more G-load. The increased G-load will also increase the stalling speed. Generally, the elevator and stabilizer have sufficient control authority to drive the wing past its stalling angle of attack, even at high speed, which can adversely affect pitch and roll control. This means that the wing can be stalled. In this case, regardless of the pitch attitude, a pilot cannot command a specific bank angle or flight path even at high airspeeds. The aircraft has entered into an accelerated stall. The wing loading must be reduced to recover from this stall and regain pitch and roll control. Aircraft with electronic flight control systems may provide protection against entering into many upset situations. These systems also assist the aircraft to return to normal flight if necessary. However, when fly-by-wire aircraft operate in the degraded mode, flight control inputs and the responses are similar to non-fly-by-wire aircraft.
The aerodynamic principles we've reviewed are applied to airplane design.
During flight testing, all airplane manufacturers exceed these parameters to help prove the safety of the airplanes you eventually fly. A working knowledge of these principles is vital to a successful recovery from an upset situation.
In this video, we've defined what an airplane upset is. We've looked at causes, and we've reviewed the aerodynamics associated with recovery. We've laid a foundation. To build upon this foundation, follow-on training should review specific recovery techniques. Different accidents, different causes, but all of these accidents do have one thing in common. At some time during the flight, an airplane upset occurred. And there's one other critical thing they have in common. The flight crews did not recover. An airplane is defined as upset if it unintentionally exceeds the parameters normally experienced in line operations or training. Specific values may vary among airplane models, but the following conditions are generally agreed upon. Unintentional pitch attitude greater than 25 degrees nose up. Unintentional pitch attitude greater than 10 degrees nose down. Unintentional bank angle greater than 45 degrees, or even within these parameters, but flying at airspeeds inappropriate for the conditions. Airplane upsets do happen, but they are rare. Because of this rarity, a flight crew that finds itself in an upset situation can quickly be overwhelmed. Causes of upsets vary. They may be caused by environmental factors, by component or equipment malfunction, by human factors, or by a combination of any of these. But no matter the cause, the foundation for recovery is the same. You must recognize and confirm the situation, disengage the autopilot and auto-throttle, use whatever authority is required of the flight controls, and you must maneuver the airplane to return to normal bank and pitch. Once you've entered an upset condition, you probably won't be able to rely on outside visual references. In many cases, you won't be able to locate the horizon. You must plan on interpreting your instruments. And if you are unsure if an instrument is working, such as your attitude indicator, you must confirm your situation through multiple sources. In fact, that's one of the reasons why redundancy of critical instrumentation is built into an airplane. This video will examine specific recovery techniques that you can use once your airplane has been upset. We've asked 3 pilots to help us in this discussion. 3 pilots who've actually been in some of the situations we'll be looking at. The chief test pilots for Boeing and Airbus have a great deal of expertise when it comes to airplanes that fly outside the normal regime. During flight testing, they regularly push their airplanes beyond normal flight parameters. For the purposes of this training, it doesn't matter how or why the airplane entered an upset situation, or what caused it. What matters most is that you understand that your reaction time is limited. In short, if you find yourself in an upset situation, you must act, and you must act quickly and correctly. You must also guard against letting the recovery of one airplane upset lead into a different upset situation.
An upset recovery team, comprised of representatives from airlines, pilot associations, airplane manufacturers, and government aviation and regulatory agencies, developed the techniques presented here. These techniques are not necessarily procedural. Use of both primary and secondary flight controls to effect the recovery from an unusual attitude are discussed.
Your air carrier must address procedural application within your own fleet structure. The upset recovery team strongly recommends that your procedures for initial recovery emphasize using primary flight controls, aileron, elevator, and rudder. However, the application of secondary flight controls, stab trim, thrust vector effects, and speed brakes may be considered incrementally to supplement primary flight control inputs after the recovery has been initiated.
One more thing. The recovery techniques we'll discuss assume that the airplane is not stalled. If it is stalled, it is necessary to first recover from the stall condition before initiating these techniques. At this point, we feel it is important to discuss stall recovery. As a pilot, you hear and use a lot of different terminology when discussing stalls. Stall warning, stick shaker, deep stalls, and approach to stalls. These are all used in daily conversation.
As we said, in some upset situations, you must first recover from a stall before applying any other recovery actions. Now, what do we mean by that? By stall, we mean an angle of attack beyond the stalling angle. A stall is characterized by any or a combination of the following:
buffeting, which could be heavy, the lack of pitch authority, the lack of roll control, inability to arrest descent rate. These characteristics are usually accompanied by a continuous stall warning.
A stall must not be confused with a stall warning that occurs before the stall and warns of an approaching stall. You have been trained to recover from an approach to stall, which is not the same as a recovery from a stall. An approach to stall is a controlled flight maneuver. However, a full stall is an out-of-control condition, but it is recoverable.
To recover from the stall, angle of attack must be reduced below the stalling angle. You must apply nose-down pitch control and maintain it until you have recovered from the stall.
Under certain conditions, on airplanes with underwing mounted engines, you may have to reduce thrust in order to prevent the angle of attack from continuing to increase. Once unstalled, continue with the other recovery actions and reapply thrust as needed.
Airplanes that are designed with electronic flight control systems, commonly referred to as fly-by-wire airplanes, have safety features that should preclude the airplane from entering into an upset and assist the pilot in recovery if it becomes necessary. However, when fly-by-wire airplanes are in the degraded flight control mode, the recovery techniques and aerodynamic principles we will discuss are appropriate. Imagine a wings level situation where the airplane pitch attitude is unintentionally more than 25 degrees nose high and increasing. In this case, the airspeed is decreasing rapidly. As the airspeed decreases, the ability to maneuver the airplane also decreases. Recognize and confirm the situation.
Start by disengaging the autopilot and auto throttle. Next, apply nose-down elevator to achieve a nose-down pitch rate. This may require as much as full nose-down input. If a sustained column force is required to obtain desired response, you may consider trimming off some of the control force. However, it may be difficult to know how much trim should be used. Therefore, care must be taken to avoid using too much trim. Do not fly the airplane using pitch trim, and stop trimming nose down as the required elevator force lessens. If at this point you cannot immediately get the pitch rate under control, there are several additional techniques which may be tried. The use of these techniques depends on the circumstances of the situation and the airplane control characteristics. You may also control the pitch by rolling the airplane to a bank angle which starts the nose down, normally not to exceed approximately 60 degrees. Maintaining continuous nose-down elevator pressure will keep the wing angle of attack as low as possible, making the normal roll controls as effective as possible. With airspeed as low as stick shaker onset, normal roll controls up to full deflection of the ailerons and spoilers can be used. The rolling maneuver changes the pitch rate into a turning maneuver, allowing the pitch to decrease. In most situations, the steps we've just outlined should be enough to recover. Other techniques may also be employed to achieve a nose-down pitch rate. If altitude permits, flight tests have shown that an effective method to get a nose-down pitch rate is to reduce the power on underwing mounted engines. This will reduce the upward pitch moment. If the control provided by the ailerons and spoilers is ineffective, rudder input may be required to induce a rolling maneuver for recovery. Only a small amount of rudder is needed. Too much rudder applied too quickly or held too long may result in loss of lateral and directional control. Because of the low energy condition, use caution when applying rudder. To complete the recovery, roll to wings level as the nose approaches the horizon. Recover to a slightly nose-low attitude, check airspeed, and adjust thrust and pitch as necessary.
Now imagine an upset situation where the airplane pitch attitude is unintentionally more than 10 degrees nose low. Recognize and confirm the situation.
In a nose-low, low-speed situation, remember that the aircraft may be stalled at a relatively low pitch, and it is necessary to recover from the stall first. This may require nose-down elevator, which may not be intuitive. Once recovered from the stall, apply thrust. The nose must be returned to the desired pitch, avoiding a secondary stall, as indicated by stall warning or buffet. Respect the airplane limitations of G-forces and airspeed. In a nose-low, high-speed situation, apply nose-up elevator. Then, it may be necessary to cautiously apply stabilizer trim to assist obtaining the desired nose-up pitch rate. Reduce thrust, and if required, extend speed brakes. Complete the recovery by establishing a pitch, thrust, and configuration that corresponds to the desired airspeed. A question naturally arises. How hard do I pull? Here are some considerations. Obviously, you must avoid impacting the terrain, but also avoid entering into an accelerated stall, and respect the aircraft's limitations of G-forces and airspeed.
We've defined a high bank angle for upset as more than 45 degrees. However, it is possible to experience bank angles greater than 90 degrees. In high bank angle situations, the primary objective is to roll in the shortest direction to near wings level. But if the airplane is stalled, you must first recover from the stall. Recognize and confirm the situation.
At high bank angles, you may be in a nose-high attitude or a nose-low attitude. Let's look at a nose-high situation first.
A nose-high angle of bank attitude requires deliberate flight control inputs. A large bank angle is helpful in reducing excessively high pitch attitudes. Unload and adjust the bank angle to achieve a nose-down pitch rate while keeping energy management and airplane roll rate in mind. To complete the recovery, roll to wings level as the nose approaches the horizon. Recover to a slightly nose-low attitude, check airspeed, and adjust thrust and pitch as necessary.
A nose-low high angle of bank requires prompt action because altitude is rapidly being exchanged for airspeed.
Even if the airplane is at an altitude where ground impact is not an immediate concern, airspeed can rapidly increase beyond airplane design limits. Simultaneous application of roll and adjustment of thrust may be necessary. Again, disengage the autopilot and auto throttle. In this situation, it may be necessary to unload the airplane by decreasing back pressure or even pushing to obtain forward elevator pressure. Use full aileron and spoiler input if necessary to smoothly establish a recovery roll rate toward the nearest horizon. It is important to not increase G-force or use nose-up elevator or stabilizer until approaching wings level. If full lateral control application is not satisfactory, you may need to apply rudder in the direction of the desired roll. As the wings approach level, use the procedures we discussed earlier for a nose-low situation. Adjust thrust and drag devices as required.
As you've seen, there are specific recovery techniques that you can use if your airplane becomes upset, no matter the type of upset. Nose high, wings level; nose low, wings level; high angle of bank. You must take control of the situation and you must react quickly and correctly. Let's review the nose high and nose low recoveries one more time, incorporating bank angles. Remember, the sequence of application of these techniques will vary depending upon the specific situation encountered. Thorough review of the causes of airplane upsets and the recommended actions you should take will help prepare you to act quickly and decisively should an upset occur.